Hey all, welcome to All About Engineering YouTube channel. I am Ajay Bhosle. Today we are going to focus on a control system. Actually, in last three videos I have covered some basic understanding about a control system, right? So now what we are going to do that first we are trying to focus on main topics on control system as perspective of IES or GATE examination or local PSU examinations, right? So among that there are five important topics, around 13 control system topics. So first we are going to hit time domain analysis, which you are now seeing on screen, right? So now we'll start that in topic, right? So what is the time domain analysis? Okay, in further lectures I will explain about frequency domain analysis and like these things, but just for understanding purpose there are different planes. So with respect to that plane we are going to do some analysis. So now we are going to study time domain analysis, right? This one. So now in time domain analysis, actually in time domains, any if you are observing any control system or any practical system, then that system response is totally divided into two parts. The first part is a transient state analysis and second one is a steady state analysis, right? So that only I wrote here. First one is a transient state analysis and second one is a steady state analysis. So first we'll go through the what is a transient state analysis. So as written here, it deals with the nature of response of system when subjected to an input. Okay, in last lecture actually we focused on some singularity functions like step, ramp, or impulse, okay, or parabola like this. So if you are giving any input among that one or another input also, like, okay, means random input. So random input maybe consist of a combination of a ramp plus parabolic like this for particular time. Okay, so if you are giving that particular input to any control system, any practical system, then that starting period means transient period is going to means we are going to observe that one in this transient state analysis, and after attaining your set value, okay, then that set value analysis, okay, that a steady state error, okay, or settling time, that this type of analysis we are going to consider under steady state analysis, right? So this is a somewhat basic understanding for this topic. Okay, means just I here I elaborate what we are going to do over here, right? So we are going to do this analysis, means we are going to observe these two state, right? So here I explain, here I give one diagram. Okay, supposedly my singularity function is a unit step, okay, like this step function, right? Means greater than or equal to 0 t function, okay, it have some magnitude. Here I am going to consider supposedly 1, and less than t less than 0, it have magnitude equal to 0, right? This part, okay, here it has a 0 magnitude like this. So supposedly one system is here, just just okay, suppose this is a system, this is a closed loop system, right? So for this closed loop system I am giving a unit step input, right? And means I supposedly I want one magnitude for this system, and I am observing output of my system. Supposedly it is showing like this one, right? So that only I am going to show here. Okay, this one, this is your nothing but your output, right? And this one is your input, this is a step function, right? So basically this output, this blue one is divided into two sections. Okay, so the first section which we are going to say it is a transient state analysis, okay, and the second section, okay, which I just elaborated is that your steady state analysis, right? So now some formulas are there, or some I'm going to take one practical example for this system, so we'll see that one, right? So before moving towards this some formulas means which which we are going to use for transient state analysis or steady state analysis. Before moving to that, first we will analyze one basic understanding. Okay, so if I am giving some transfer function for you, okay, transfer function is nothing but your Laplace transform of output divided by Laplace transform of input at in all initial conditions should be 0, right? So if I am providing, or if any examiner is providing the transfer function to you, then what you have to do? So first you have to understand what is the type and what is the order of the system, okay, for this transient state analysis, or because this order and order of system and type of system majorly contribute to your transient state response and steady state response. That's why it is very much important to understand these two topics, right? So first we'll see what is the order of system first. Okay, first I am going to elaborate what is the type of system. Okay, so to know that this is just example transfer function, right? So these are nothing but your zeros and these are nothing but your poles. Okay, and this pole, this just second, right? So this pole you have to focus, right? So what it is, okay, here it is written that s to the power p, and p should be, p may be 0, 1 or like this to n order, right? So if I am considering p as a 2, so what it means 1 divided by just 1, consider 1 here over here, right? So what it means, 1 divided by square. So these are nothing but your poles, okay, and poles means s is equal to 0, right? So you have two poles at the origin, right? That you have to understand. This is suppose I am drawing this s plane, this is a imaginary axis j omega, and this is a real axis sigma, right? So these poles are nothing but at your 0, okay, at your origin, repeating poles at your origin, right? So it means that, so type is nothing but that only. Type is if you have one system, then type of that system is nothing but your poles, means number of poles at your origin, right? So if for this example, if in case I am taking 2, then type of system is equal to 2, right? So for knowing the type, definitely your transfer function should be open loop transfer function, right? Okay, so you are able to know that open loop transfer function. And if you want to know the order of system, okay, this second topic, this one, order of system, then what you have to do, you have to form the characteristic equation, and you have to note that order of that characteristic equation. It may be like this. Supposedly I am considering second order system, then equation just you have seen maybe in some examination you have seen that this is a standard example for second order system characteristic equation, that is nothing but s squared is equal to 2 zeta omega n s, okay, plus omega n square, okay, right? So what it means, this is nothing but your characteristic equation for your second order system. So it means that the order of your system is a 2, right? This, right? So this, so characteristic equation order, okay, means characteristic equation order will is providing your order of system, and open loop system poles at origin are providing your type of system, okay, right? So this is just a basic understanding, but it is somewhat important, right? So you have to remember this point also. So now we are moving towards one practical example understanding. Okay, actually it is somewhat interesting. Okay, because now what I am doing, I am relating my theoretical knowledge to my practical knowledge. Okay, so this example will provide much more knowledge. Okay, so now you have to focus on this, right? So first I will elaborate what I am going to consider, right? So just for example, just take it as like a series DC motor, right? Series DC motor, this is nothing but your series DC motor, right? So series DC motor consists of your stator windings, right? This is nothing but your armature winding, right? So these are a stator winding, these are a armature winding, and this is your supply. So and this motor, so why we are using this motor to supposedly, for example, just you are using this motor to rotate conveyor belt like that, okay, or to pull a bucket of water from well like this. You can consider anything, okay. So this is a mechanical representation of that system, right? So I will elaborate this system also and for motor system also. So first what I will focus on motor system electrical parameters, then I will focus on mechanical parameters, okay, and finally I am going to collaborate these two parameters and we'll try to get one transfer function, right? So first what I am going to do, just take it. So what I am going to do, I am going to apply one voltage over here, right? This E voltage, okay. So these are nothing but the stator winding, right? And this part contain your uh, armature winding. So now what we are going to see, first I will apply a KVL for this total circuit, means for electrical circuit. So E is nothing but applied voltage, right? So E is a provided voltage E. So this is a rotating current in this mesh, right? This is nothing but mesh circuit. So I into R, voltage KVL is nothing but the summation of your voltage drops across each element, right? So I into R, that I have noted here, and then voltage drop across L, that is nothing but VL is equal to L di by dt, right? That I think this is simple only, and this is the your voltage drop, right? So I wrote here that only, and this is nothing but your back EMS which is generated in DC motor, okay. So for back EMF, just for understanding purpose, back EMF, what is the back EMF? EB is directly proportional or directly proportional to phi p n z by 60, right? So 60, this A is nothing but your parallel path, right? This is 60 is a constant, Z is nothing but your number of conductor, N is the speed of your machine, any machine, okay. In this case it is a motor, okay, so motor speed, and P is the number of poles, and this is the flux density at your pole, okay, flux density at your pole, right? So now what I am doing, I am transferring this EB to my left hand side. So equation is E minus EB is equal to IR E plus L di by dt, right? So now what I am going to do, just I am transferring this T plane to the S plane, right? So LS, this differentiation means 1 S, because power is a 1 here, so S only, okay, L into S. So I am taking IS common from this total equation, so IS into L R plus L S, right? So from first understanding you understood that this is a first part of total equations, okay. And just now I wrote that your E is equal to directly proportional to the N, right? So this is the second part, this is the first part, okay. Just yes, here I have mentioned over here. And now what I am going to do, this V, so what EB is directly proportional to V means velocity, okay. V means velocity, means that is only represented in last which I shown in a green color, that I over there I represented it as a N, but here now I am representing that speed with symbol V. So to replace this directly proportional symbol I am taking one constant, okay. So now I am changing the directly proportional to the equivalent symbol, okay. So EB is equal to KTV, right? And now this I am converting this time domain to the S domain, so this is nothing but your second part EB, right? So now we move towards the third part, seeing this third part, right? Look, this one. So what it here means, the force which is generated, it is directly proportional to your armature current, right? Means the current which is flowing to the armature, that is only responsible to generate a force on your motor shaft, right? So now similar I am going to replace directly proportional with a Ki, This is your third part. Okay, so now what is our mechanical system? So first we'll see the mechanical system. With that I am elaborate this total equation, right? So just we'll focus on that system. So this is nothing but your mechanical system representation, right? This part. Okay, so what it is, I am going to elaborate now. Actually in part 1 2 I have explained about electrical system. Now in part 3 I am going to explain about mechanical system. So this is a mass m, right? This is a velocity, this is the applied force. Okay, this is nothing but your applied force, this is a velocity, this is your mass, and this is your friction. Okay, k, spring constant, you can call it as a spring constant, and this is your damper, okay, which is represented by b symbol, and this friction constant. So now we are going to form one equation. Okay, means f force is as a input, and this total system we are equating with respect to your input, right? So this is nothing but your mechanical equation equivalent for that total system. Okay, so F is applied force, and F is equal to m into a, force is equal to mass into acceleration, like that. Okay, so what you are doing, this m into dv by dt. If it is this is a velocity, if it is just a displacement x, then what it is, m into d square x by dt square, right? Like that. Then this is your damper winding, so b into v. If it is a displacement instead of this v, then it will be b into dx by dt, and this is a spring constant k into x in displacement concept, but here it is a velocity, so you have to integrate v, right? So here I have converted my t domain to s domain, whichever we have seen that f is equal to m dv by dt bv plus k integration of vt. Okay, right, that equation only I am going to convert into s plane. Okay, so as you know that with respect to Laplace transform, with the help of Laplace transform, I have converted this equation. Okay, so what I am going to do, I am taking s as a common over here, and just taking LCM. Okay, right. So we have four equation. This one is this is a one equation. Then first equation is E minus your EB is equal to your IS into R plus SL. Okay, so what it is, E minus EB. Okay, this is a minus symbol, and your just I will show that equation, right? So look these three equations. Okay, this EB. Okay, so what it is, so you are providing this one, right? This is you are providing, means this as an input and this is as an output. So transfer function means output divided by input. So I of s is equal to divided by this difference, total difference E. I am replacing it E. Okay, so what it is, like 1 divided by r plus ls, right? Correct, r plus ls. So this one equation. Then second, what it is, what you are doing, this is your output and this is nothing but your input. So output v divided by e is equal to your 1 by kt, right? 1 by kt. Here I am going to use, this is the second equation, and this is third. Okay, so what you are doing, you are giving I of s, and you have output as your force. Okay, so 1 by k dash, right? This is equation third, right? Now we'll see the equation 4 understanding. So this is nothing but equation 4, right? I will clear this one. Okay, right? So this is equation 4. This is nothing but your output. Okay, right? And this is nothing but your input. So you have to transfer this equation to your left hand side, right? So just what I am arranging from first equation, E minus EB is equal to 1 divided by R plus LS, and this is nothing but your output. And from equation 3 you are going to see that f of s is directly proportional to k into I of s, like that only. And this is nothing but your equation number 4, representation. Okay, v of s divided by f of s is equal to s into m a square plus bs plus k. That only I'm going to replace. And this is nothing but equation number second representation, right? So finally, if you are going to take the total transfer function, okay, it means open loop transfer function for the system, then it will be like this. You are going to multiply these total systems and like this. So what it is now, what you are going to, just I told that just we'll try to apply our type and order concept over here. Okay, so this system, this total system, open loop system, for type you have to take a open loop system of that total system that with respect to that system, right? So in this system, this is in this system you are able to see that here s to the power 0 means it is a 1 only. So you have 0 poles at your origin, so type is a 0, right? Understood. And for order, you have to, what you have to do, you have to write characteristic equation. So characteristic equation is represented by 1 plus g of s h of s. In root Harvard's criteria, I will elaborate some more points on this characteristic equation concept, right? So just for sake of purpose, just try to remember this one, 1 plus g of s h of s. So this is nothing but g of s h of s. Just what you have to do, you have to take it as a 1 plus 1 here, 1 plus, so you are going to multiply with this one, and this is your constant term, right? That only I am going to replace. So what is the order? If you are multiplying this s over here, then it will be s cube. Okay, this, so order is s cube. So what is the conclusion for today's class? So today's class we just focused on a basic concept of transient analysis, steady state analysis, what it is, and up to what time it will appear. Okay, then we focused on how to calculate type and order for any system, and then we saw one practical system, right? That series motor and one mechanical rotor, right? So actually just go through this lecture and try to analyze this total system, means you can analyze other systems also, right? So take care, right? So we'll see in next lecture. Bye.